Okay, let's get started. Let's see if this thing's working. Oop, switch to this guy. Good. Okay. Hi everybody. Welcome to the last day of week 1 of Data 100. 7 more to go. Lab 1's due tonight. Make sure to pass all the public tests. We have more assignments now picking up, and there are also going to be more assignments released extra early. We just released 2A, Lab 2A and Homework 2A, about 6 days early. So we're almost at our sort of week ahead or more early. We're getting there. Homework 1 is due tomorrow. Highly recommend you start working on it. Remember the slip day policy. Take a look at the syllabus for it. But this summer is going to go by fast. So try to stay as close to schedule as you can, and your future self will thank you. Pre-semester survey is due tonight with the graded discussion option. Hopefully you went to discussion yesterday to get a better sense of whether you want to do discussion this semester. This weekend, we'll assign folks to a discussion section if you choose the graded discussion option. And as usual, just notifications about office hours. My office hours and Michael's office hours are always going to follow our lecture. You can just walk with us a couple meters away in B1. And then staff office hours are most days of the week in Warren. Nice air-conditioned building across campus. Great place to just do your work, do your homework, do your labs. There will probably be TAs there intersecting the time you're there. They are there most of the week. Okay, and with that, let's go ahead and get started on today, our sort of capstone pandas lecture, where we're going to be talking about grouping, huge part of the data science workflow. I really cannot stress enough how big of a part of the data science workflow this is. This is one lecture, but at least in like my work, this is, of the analysis I do, 80% of my time. No joke. It's just like this idea of grouping and aggregating. So understanding this really well is very important. And it takes a moment to sort of get the hang of how to think about things as group by and an aggregation. So if it's your first time seeing this, not a problem. I'll start with this split, apply, combine paradigm. So this is totally language agnostic, totally doesn't depend on a language. This is a very powerful way to summarize trends in a data or perform computations by group in a data. If you ever see this idea of split, apply, combine, the idea is we have some data set. Here's our data set on the left. We can see it's a simple data set, just 2 columns. We have some group identifier and also the age of the person. We're splitting based on some column in the data set, some identifier in the data set, in this case group. So notice we've now split into these little subframes. We start with our main data frame. We then go to these subframes. That's a term I'm going to be using a lot today. We apply some function to the remaining columns in that subframe. So for example, we apply the mean to that age column, and then we combine all of those subframes back together to form a new summarized data frame. This is essentially summarizing the entire lecture without mentioning pandas. Okay, split, apply, combine. This is something you saw in Data 8. Today we're going to see how to do it with pandas. So the function for performing groups or splitting in pandas is called group by. You'll be using that function a lot today and in your future data science career. So group by will split a data frame into these mini data frames. Like I said, these little subframes are these little SFs. Confusingly, SF looks like San Francisco. SF we'll use in the class as sort of anytime we're referring to a subframe of a data frame that's been split. So notice what happens. We call group by on some original data frame, and I'll give you more precise syntax in a minute here, but we call group by, and we specify the column we want to group on. And then under the hood, critically this is under the hood, the data frame is getting split up into these subframes for each year. Okay, it's not physically separating those rows of the data set or giving you separate data frames, returning back separate data frames. This is all sort of implicit tagging going on under the hood. So pandas is aware that you're grouping, okay? And these are all stored in something called a group by object. We'll see this object in a little bit, but you rarely, I mean, almost never, I don't think in analysis I've never had to actually directly work with a group by object. Okay, this is a critical step to actually group your data, but something always comes after, whether it's an aggregation or a filtering or some transformation that you're applying. But this first step of grouping is critical. Okay, so group by will let you actually group your data frame. In this case, by 1 column year. You can group by multiple columns. We'll see that towards the end of the lecture today. So then after group by, what you're most commonly going to be using in Data 100 is something called .ag or essentially .ag under the hood. So what does .ag stand for? It stands for aggregate. It stands for aggregate. It's going to apply some function to each of those subframes and then combine them back together. So it performs both the apply step and the combine step. So take a look here. Take a look here. So we've got the original data frame. We use .groupBy to perform the splitting step. This was on the previous slide. So that splits our data. And then .ag, we specify some function, sum, that's going to sum up all of the rows in each of the subframes. So notice in the subframes, we're summing up these numeric columns. You may be wondering, well, what about the other columns? That's an excellent question. That'll be answered on the next slide. Okay, but we're summing up those numeric columns in the subframes, and then we're getting back a new data frame for each year. So each group gets one of its own rows here, and then it has the sum of those columns. And like I said, this is an incredibly powerful tool. Incredibly powerful tool. It might seem simple here, but when you're performing this with thousands, tens of thousands, hundreds of thousands of groups, right? Customers, some unit of analysis here, products, you can do all kinds of crazy things. And this is often most of data science. Okay? All right, so let's keep going here. And how do we actually write the syntax? So before we sort of had a high-level diagram, you could see a little bit of syntax here, but what's the actual written out syntax for grouping? So what we do, you'll be writing this out almost exactly many, many times. We start with our data frame, our DF. We start with our data frame. We do .groupBy. We specify the column we want to group by. We call this the grouping column, the grouping column. And then it's a little bit tricky to get used to at first, but you'll get used to it, and different languages have different ways of doing this. We then specify which columns we want to aggregate. Okay, so that first column is the column to group. Okay, and these are the columns, you might have more than one, to aggregate. In this case, just the count column. You might be wondering, why is that in double brackets and not single brackets? It would work in single brackets, we'll see in a minute. Kind of like before, if we use single brackets, we'll get back a series. If we use double brackets, we're going to get back a data frame. Don't worry about that detail for now. Most important thing is just to recognize we're selecting which columns to aggregate. And then finally, we say, okay, well, I want to aggregate using some function, and in this case, the function name is actually sum. We're summing, but we could take a mean, we could take a min, we could take a max, we could write a custom fancy function that we're going to apply to each of those groups. Okay, so let's see this in our diagram. Move this over here. So, don't highlight, erase. There we go. So look what's going on here. Okay, we're grouping by year. We're selecting that count column. Okay, so that's telling us just look at that numeric column. Okay, if we don't specify that column, the code may still run. We'll see in a minute what could happen. Okay, and then we get that same result we were looking at before. Okay, so you'll be writing a statement like this many, many times in Data 100, at least 100 times. Okay, let's keep going. This is also on the reference sheet. Just as a heads up, this is on the reference sheet. Another thing that's on the reference sheet, if you haven't already looked at the reference sheet, I recommend looking. It's not detailed documentation about each function, but it's enough to sort of remind you what is the syntax and what does something generally do. Again, we want you to focus on understanding what these functions do. The precise syntax you can sort of offload onto the reference sheet if you'd like. You'll end up memorizing a lot of stuff just on your own as you work through it. Okie doke, there are other aggregating functions aside from just sum that we can work with. What can we do instead of .ag? So we have lots of other functions at our disposal. There are inbuilt Python functions, okay, sum, max, and min. We used one of those just now. Some of these are on the reference sheet. We can also specify things in different ways. So notice we would have gotten exactly the same result if we wrote .ag np.sum. We would have gotten exactly the same result if we wrote .ag with sum in quotes. As usual, there's many ways to do the same thing in pandas. It kind of comes down to personal preference, okay? And then also some functions can be just called directly without even using ag, and pandas knows what you're doing. So we could have actually written .sum here with parentheses. That would have worked just fine. So there are some common functions that are used so often, mean, size, we'll see in a minute, count, sum, min, max, that they're just implemented as just mean with parentheses next to it where you don't even have to write ag. Okay, Now, do you have to memorize all this? Again, no. You'll get used to your sort of favorite way of coding as you work through things. But you can already see there's like 4 ways to do exactly the same thing here, and there's probably more. Okay? All right, so that's the group by and aggregate sort of overall summary. We'll go into more detail over the course of the lecture. So let's actually do our sort of first bit of, I'd say, real data science here. We're learning about data science tools in this class, but we haven't really played with a sort of real data set and gotten a real result yet. So let's actually take that baby names data set, which you might recall are all of the baby names from kids born in California up to about 2022, starting pretty early. We're going to group by year. So I would read this. I'm going to compute for each year the sum of the count column. Okay, for each year, anytime you see the words for each, that's a hint you should probably use grouping. Okay, for each, for every year, I'm going to compute the sum of the number of babies born. And so we get this data frame on the right. Kind of hard to see patterns already here. We know that it's gone up since 1910, which makes sense. But if we actually plot this, and plotting something we're going to learn more about next week, so don't worry too much about the plotting syntax here. We're using a package here called Plotly Express. Plotly just lets you make interactive plots. We'll see this a lot in the class. But if we plot this graph, we can see some interesting patterns, right? We see the baby boom right after World War II, right? We see there's like seems to be another boom in the 80s. I think a lot of that might have been immigration. But we can actually see in the last, more than 20 years here, almost 30 years, there's been appear to be decreasing number of births in California. Okay, and again, that assumes we trust this data, that it contains all the information that we actually need, right? Lots of assumptions sitting on top of what we just came to the conclusion of, but we're seeing pretty clear patterns. Okay, all right, let's keep going. So we're gonna do Slido, but I just want to like set up the mystery for you to start out here. Let's say we have some data frame that just is named column 1, column 2, column 3, super exciting. And what we're gonna do is we're going to use group by. We're gonna group by column 1, and then I'm just gonna write .ag max. I'm not gonna include anything else. Group by column 1, .ag max. And that data frame on the right may exist, it may not exist. The code may run, it may not run. I want you to think for a minute, and feel free, as usual, talk with your neighbor. What do you think is going to show up in that first row? What do you think will show up in that first row? Give that a go. If folks have questions, I'm happy to come around. Just raise your hand. And I also forgot to open up the Smarties, so let me do that now. So, sorry if there's the little noise in the speakers. I don't know what it is. My mic is off and it I don't know, are people hearing that little chatter in the speakers? If you are, sorry about that. I'm going to ask the lecture folks about that. Because notice that even if I turn off my mic, I'm going to leave this up. Feel free to keep talking. I'm just going to switch over to the demo so we can actually work through the problem. As usual, all the Slidos are implemented as part of the demo. So I highly recommend having the demo open, especially during these code-heavy pandas lectures. Okay, so we're just importing the NumPy, Pandas, and Plotly packages for that plotting we did before. Again, lots of complicated code here. Don't need to worry about this for data 100, but take a peek if you're interested. This is just importing the baby names data. This is just importing the baby names data. I'm going to skip ahead. This is everything we just did. We're now at the Slido exercise. Okay, so the goal here is to try to predict what's going on with this group by operation. And so what we've seen before is we always grouped by some column. Okay, and then we specified which column we wanted to aggregate. And then we said aggregate using some function. But in this case, we didn't specify which column to aggregate. And the question is this going to run? Is this still going to work? So let's actually go see what happens and dissect it a little bit. So here's our data frame. Let's try that one more time. Maybe not. Hold on one sec. Hold on. Okay, here's our data frame. Okay, we have column 1, column 2, column 3, just like the example. And then let's just see what happens when we run this code. So we get warning. Okay, something is weird going on. That's fine. Anytime your code still runs, you can always look below. You don't have to be scared of warnings. Read it, see what's going on, see if you need to change anything. They'll sometimes say things will change in a future version just to help you out. But notice this actually runs. This actually runs. We get column A, B, C, right? We get column 1 with A, B, and C here. And then we can see that both columns somehow have been aggregated. So the largest value in A appears to be 3, and we can confirm this. If you look at all the A's, A is 3 here, A is 1 here, A is 2 here. So indeed, that seems to be working okay. So 3 is correct there. But then why, when we take the maximum of strings, are we still getting a result here? And the idea is when we order columns by values, when they're strings, they're just going to be alphabetized. So the max of a string is just going to be the last thing alphabetically, So if we look at all of the A rows, we have AK, okay, we have HI, and we have CA. H is the latest letter in the alphabet of those 3 starting letters. And so if we look at our output here, HI is indeed our max. Yes, Maxime. Good question. So if we had mean or sum here. So sum, I don't know if sum would work. I know you can add strings, right, in Python, so they would all concatenate. Mean, I think, would give us some trouble. Let's actually see. I have a feeling that would give us an issue. So we run mean. What happens? Mean is not defined. That's not very helpful. Let's do np.mean. Okay, what happens? Get an error. How do you take the average of a string? You can't. Great question. Let's try sum. Let's see if it works. np.sum. NumPy, I don't know if that will sum up the strings. Yeah, it will. Okay, so numpy.sum, notice the strings just get concatenated with each other. Right? Is this a realistic use case? We don't know, but yeah, great question. Great question. Okay, so just so you know, if we don't specify which columns to aggregate, Panda is going to attempt to aggregate all of them. It's going to attempt to, you can essentially just think of it trying to aggregate every single column. So notice at the bottom, if I run this with column 2 and 3, if I run this with column, we will hide video panel, hide floating mutuals. Okay, not sure what happened there. Okay, but notice, let me unblink the screen here. If we run this with column 2 and column 3, specifically labeled, we get the exact same result. Okay, so this is shorthand for aggregate all columns. Now, I always like to be really explicit in my code, right? When I'm reading some code that I wrote a year ago, I want to know what I was talking about. And so I would prefer to actually say what you want to aggregate as opposed to just aggregate everything. but just know like it still works. It still works, right? Looking at these like corner cases helps us understand the functions better, even if those corner cases aren't showing up in our work very often. All right, let's return to the slides. Okay, great, great. You can see it's confusing. You know, I would have gotten this wrong back in the day when I was learning how to do this. But now you know. Okay, let's keep going. All right, so if you don't specify which columns to aggregate, it's going to aggregate all columns like we just saw. This is exactly the same thing from the demo. Okay, here's just a visual of what just happened, sort of connecting to our visual from earlier. We can see that we have the group by step under the hood, everything with A, everything with B, and everything with C is getting put in its own subframe, and then each of those subframes is getting aggregated together based on the max function. Okay? And this pattern we're going to see over and over and over again. All right, so let's try another mystery here. Let's try another mystery. Our goal is to find the baby name with sex equals F that's fallen in popularity the most in California. One really interesting thing about data science is like you'll hear the words fallen in popularity the most, and you kind of nod along, and you're like, okay, yeah, we can do that. But think for a minute, like, what does that even mean? What does fallen in popularity the most even mean? And your job as a data scientist will be very often to take the metrics that, you know, a product manager or somebody else sort of tells you, and you sort of understand intuitively, but hasn't been defined really rigorously. Think for a moment, like, what does fallen in popularity the most mean? Is it in terms of like the absolute count of names? There was like a really high count at one point, and the decrease is really big. Is it like a percentage decrease, right? What sort of years are we sort of comparing here, right? What if a name was really popular a long time ago, it became not very popular, it became popular again? What does fallen in popularity mean in that case? So one thing you want to do is when you hear sort of quantitative terms like this thrown around, like fallen in popularity the most, you want to think like, what are we even talking about? Because it's very easy to just like accept this as true. My sort of favorite word in statistics that people use all the time is like, I'm really confident about this, I'm really confident about that. But like, what is confidence, right? What are these words that we sort of throw around mean? Okay, something to think about. So female baby names, we're going to go grab all of the baby names where the sex is female, okay? So we're indexing into the baby names data frame using that context-dependent extraction, grabbing all the rows where the sex is female, and then let's go count up the number of times Jennifer shows up. Let's go count the number of times Jennifer shows up. So we're going to do that Boolean indexing again. We're going to go to female baby names under the name, and we're going to go grab all of the rows where under female baby names, the name is Jennifer. We did this because there might be male babies with the name Jennifer in this particular data set. We're filtering to female babies in this case. Okay, and then we're going to grab the rows where that name is Jennifer, and we're going to grab the count column. And we do this, and we plot it, and we see another interesting plot. Baby names data is like notoriously very fun to explore. You can look at your own name, you can look at your parents' names, but we can see that Jennifers were very, very popular back in the 70s or so. Does anyone have a parent named Jennifer here, by any chance? No? Brother, sister named Jennifer? No? Aunt named Jennifer? No? Okay, not a lot of Jennifers here. Okay, but we can see lots of Jennifers in the 70s. Okay? You can do this for your own name. Like I said, feel free to take a look at the demo. You can put your own name right in and see what you get. And so like I said, what is popularity? How do we know if a name has fallen in popularity? Because it does look like Jennifer has fallen in popularity pretty substantially since the 90s. Okay. So what is popularity? What is popularity? Let's propose a metric. There's no correct metric here. You're going to be dealing with a lot of ambiguity as a data scientist. What is the sort of correct metric? There isn't one. We need to use our own experience to think of one. We need to use our own context. So what about we make up a metric called ratio to peak? Made up metric here. This isn't something you need to memorize. So ratio to peak, we're going to say as the ratio to peak for a given year is take the number of babies with a particular name like Jennifer born this year and divide by the maximum number of Jennifers born in any year. So what's the ratio from this year's number of births to the maximum ever? Okay, so for Jennifer, in 1972, we hit peak Jennifer. There were 6,000 Jennifers born. In 2022, there were only 114 Jennifers in all of California, state with, you know, almost 40 million people. Okay, the RTP, the ratio to peak, is 114 over 60/65, about 0.02. right? We're at about 2% of the maximum number of Jennifers that have been born at any time. Okay, Jennifer Garner was born in 1972. I was looking up famous Jennifer. That's one. Okay, let's keep going. So we can compute this with pandas. So the maximum number of Jennifers born in any year is just the maximum of that series we had earlier with all of the counts of Jennifers that were born. And then the current number of Jennifers that were born, we could grab from all of those counts by looking at the very last element of that list. So notice we're using iloc on a series here. It's amenable to a series. And if we index -1, that means start at the very end, right, and move sort of one backwards. Okay, so when we index to -1, that means the very last element of that series. And just as a reminder, our data was sorted by year. So this would imply we're grabbing the count of Jennifers from the very last year in the data set, 2022. Okay? And so if we look and calculate that ratio to peak metric, we get that 0.019 we saw before. Again, what does Python give you? They give you all these decimal places. If you were reporting this in a newspaper or an article or a blog, do you need to give all of those degrees of precision? It's not helpful for anybody, but it's a very common default when you're first learning to just copy it in and feel like you're giving something really precise, right? You want to think about who's sort of reading your work, right? You want to have empathy for the other person. Okay, so we can actually just define this as a function, which we're going to use in a group by momentarily. So if we have some series and we want to compute the ratio to peak of that series, we can define a function where we take the last element of that series. So this is specifically defining ratio to peak for the very last element of the series. And we're going to divide by the max of that series. And if we apply this function just to show you that it works, we can apply this again to our counts of Jennifers over the years. Okay, all the way up to 2022, we can see we get the exact same result. Okay, so we just defined a function, something you've seen before, 61A, 88C, some other coding class. Okay, and so now let's actually do this with a group by. So we're going to take our custom function and actually use it with group by. So what's so nice about group by? We don't have to go through and repeat the process we just did over and over. We don't have to do it for Jennifer. We don't have to do it for Deborah. We don't have to do it for Susan, right? We don't have to keep going through all these names one by one. Group by is really nice because it'll just do it for all of the unique values in your data set all at once. All at once. Okay, the simultaneous action is very computationally nice, and then just having to write all this code, right? You can condense lots and lots of code into essentially one-liners. So we're going to start with our female baby names. We're going to group by each particular name. So for example, for all the Jennifers, for all the years with Jennifers, for all the years with Deborah, for all the years with Susan, we're going to grab two columns, the year column and the count column. You'll see if this makes sense on the next slide. And then we're going to aggregate by applying the ratio to peak function to each of these columns. So we say what we want to group by, which columns we want to aggregate, and how we want to aggregate them. All right, and there's that ratio to peak function again. So we can do this, and we get back a data frame sorted for us, kind of nice, sorted for us. So we have our names. So for this name, Adini, we can see that the ratio to peak is 1. The ratio to peak is 1. The very last count in the data frame is the same as the maximum count in the data frame. Any guesses why that might be the case? How would we get 1 in this case? Yes. Let's say it just showed up in 2022. Exactly, this name has only showed up once, right? And so the maximum, the actual value over the maximum is exactly the same as the value we have, so we end up with 1. Great. But you can see for other names that are maybe more common, Ziania showed up probably in more than 1 year, right? We don't have that same value of 1. And we can see there's lots of other names here, maybe some more common names, okay? But I do have a Slido for you, a little bit of a mystery, because we look at that year column and they all look like 1, at least what we're looking at, right? We never want to make the assumption that the preview that we see is necessarily representative of the whole data set. But why don't we think through this? Why don't we think through this just for a minute as sort of a sanity check, right? Are all of the rows where year is now, oh gosh, don't look at that. For all of the rows where, again, don't look at that, hold on. I guess that's not going back. Okay, all right, think about it for a little bit. Again, most important thing is understanding why, not necessarily getting it right here. Okay, are there any rows where the year is not 1? You may already know the answer, that's fine, but convince yourself why that's the answer. Why is that the answer? And again, feel free to talk with your neighbor. Raise your hand if you got questions, I can come around. So we saw that the answer was the last one. Maybe think for a minute, why would every row have year equals 1 here? Why would every row have year equals 1? You might want to look at the code that generated this table. And also think about the structure of this data set. Leave the poll live, but let's go ahead and check out the demo here. So let's go take a look at the Slido. So female baby names. Gosh, why is that not working when I just want to click there? You'll learn if you ever start lecturing that the rule of lecturing is everything breaks when you lecture with near certainty. Okay. All right, so we have our baby names data set. This is just filtered to all of the rows where sex of the baby is female. And then keep in mind, baby names is already sorted ascending by year. Okay, it's already sorted ascending by year. Generally, when I do data science, I don't like to rely on the fact that my data set is sorted in a particular way, unless I make that assumption really, really clear at the top. I like to write my code so that my results are sort of agnostic to the sorting, but keep in mind here, everything is sorted by year. So we're in increasing order. What does each row here represent? A row means for a particular sex, in a particular year, for a particular name, how many people were born, right? And then we're increasing by year here. We're increasing by year, and it looks like the names might be kind of alphabetized in some of the years because we're seeing a lot of Z's in 2022. These don't appear to be alphabetized. So it does seem like we're increasing by year though. Okay, so if we look at all the unique values in the year column from this RTP table that we generated before. So this is from before. We grouped by name. We said we want to aggregate the year and count columns, and we're going to aggregate using this ratio to peak function. So we're going to take the very last element of the series and divide by the maximum value in the series. Okay, if we look at that year column in that RTP table, and we look at all the unique values, we get a single value 1. So it does look like every single one of these is 1. The question is why? The question is why? So again, if we look at this data set, it's ordered by year. And so for each name, the very last year is going to be 2022. What's going to be the maximum year for each name? 2022, assuming someone was born in 2022, right? Let's say the name stopped appearing in 1950. The maximum year is going to be 1950, right? And the very last element is also going to be 1950. But that's just because the data frame is sorted. If we were to randomly shuffle the data set, okay, so look what's going on here. I'm saying sample from the data set, and instead of giving it a number to sample, I'm saying the fraction I want to sample is 1. So sample 100% of the data without replacement. That's effectively just resorting the data. Nice little hack, right? So we're just resorting the data here, and I'm going to perform exactly the same group by operation. And if I do this, notice now the years aren't all one. Okay, they're not all one because it had to do with how the sorting was working. Our code was sort of dependent on that initial sorting. Okay, all right, that's Slido 2. I think that takes us to our first interlude here, our first and only interlude. Great, good. Okay, not worried about this. Not worried about this. We talked about, oh, let's see, actually, I'm gonna talk about this. Okay, so keep in mind, like, was it very useful to aggregate the year column? No, right? It happened, we saw it, we dissected it, we understand grouping better, but we didn't really need to aggregate it. So we want to specify what we should actually aggregate. And the thing we want to aggregate here is count, right? That's what we really care about. That's the real RTP, ratio to peak metric here. But there's something kind of confusing about this data frame out of context. Is that count column a count? No, right? It's correct. Those are all like the numbers we actually wanted, but it's labeled with count. That's not very helpful, right? This is sort of like the human readable side of data science. Just because the code works, we want to be able to actually read our code. So let's go ahead and rename that column. How do we rename a column? Rename function from last time. So let's take our result, that RTP table, okay, that we got, and what we're going to do is just rename it. This is exactly what we saw before, and we just pass in a dictionary, again, where it's very easy to confuse what should be the key and what should be the value. Try them both, just see what works, right? For every time we see the count column, we're going to rename it count RTP, and that's much more descriptive now. Okay, so just a useful thing to do after grouping. Okay, we can also do a little bit of data science here as well. So we've computed this count RTP now for every single one of the names, Debbie, Deborah, and we've sorted. So it looks like the biggest difference from now to the very maximum was for this like Debbie and Deborah name. Anybody have a mom named Debbie or Deborah? No? Any aunts named Debbie or Deborah? Maybe not. Okay, but it looks like that's the largest gap here. Okay, and so if we plot Deborah, you can see, peak Deborah was in like the mid-50s, right? Peak Deborah was in the mid-50s, but basically nobody is named Deborah these days. Okay, it's not zero. Somebody was named Deborah, but it looks like probably like one person, right, out of all of these. Okay, and we can do this for many different names. We can get like one of these nice spaghetti plots, which when you're doing internal exploratory data analysis, it's kind of nice to read this. I can actually go take the time to go try to align those colors. Okay, depending on color blindness status, that might be harder for folks, something to think about here. So again, these kinds of plots are like really cool looking, but when you think about publishing these kinds of plots, your readers have a limited amount of time. Do they really want to take the time to go line up all of those lines? You should probably think about a better way to plot. Okay, so this is something we'll be thinking about when we get to the plotting lecture, this idea of sort of building empathy for the person looking at your work. But you can see all of these names, these sort of top names with the largest decreases, all have the same pattern, where they had a very high number of folks born with that name a while back, and then now basically don't have anybody with these names. I know lots of friends' moms who have these names. I think I can name each one. Okay, let's do an interlude. 2 minutes. If you got questions, I can come around. Otherwise, take your 2 minutes, stretch, go to the bathroom. See you in a bit. Where did the Smarties end up? The back? Did anybody not get one? I know they were sort of passed around haphazardly. Maybe I'll walk around with them. Oh, hey, what's up? Hey, Meenakshi. Thank you. Appreciate it. Anybody on this side? Yeah? Good. All right, we ready? Let's dive back in. We got some more stuff to learn here. Okay, just some things to mention. Raw group by object. So I hinted at this before. If you just run a group by with nothing else, notice if we look at the type of that group by object, it's this special group by object. We see this like pandas.core.groupby. If you ever see this, it just means your data set is grouped, but it hasn't been aggregated. Under the hood, all that grouping is happening, but you need to do something with those groups. Aggregate, filter, we'll see in a minute, or some kind of transformation or sorting. Okay, so we can use lots of different functions. .ag is only one of the choices. So we've seen some of these already, where we can, instead of writing .ag, compute a mean, sum, min, or max. I swear there must be a mic placed somewhere that's making that sound. I'm so sorry for that sound. It's driving me nuts. Okay, so we have mean, sum, min, or max. We also have some other nice functions that we can use, like first, identical to getting head 1, right? Just one value from the top. We can get the last element. And then we can get the size or the count. What's the difference between those? That's kind of mysterious. What's the difference between size and count? We'll see in a minute. A little bit of a pet peeve of mine. Or we can also filter, which is super powerful. The filter is super, super powerful. So we'll play with that in a minute. But let's start with the size and count. And then there's more in the documentation. You could take a look. But let's take a look at size and count. So if we group by year in some data set, and notice now we're throwing in some NaNs, missing values, so we can play around with these a little bit. So if I group by year, same as before, we're just getting groups by each year for each unique value of year. And then if we use the size method, what ends up happening? Size is just telling us how many rows are in each group. So we have 2 rows here, 2 rows here, 4 rows here, and that's exactly what we get on the right. This is super, super common, just counting up the number of elements in each group. A lot of languages just have a single function for doing all of this because it's so common. You don't even have to write group by. Okay, in R, you can just write count and it'll do all of this because this is such a common operation. Very similar to value counts. Very similar to value counts, which is kind of, like I said, the sort of shortcut operation for doing this under the hood. We were secretly grouping in the last lecture when we learned about value counts. But notice we don't get sorted here. I guess you can't quite see that we didn't get sorted here. Oh yeah, no. So notice we're 224 here. If we did value counts, we would get 422. It would automatically sort for us. Okay, again, multiple ways to do exactly the same thing. Okay, now if we use count, things look a little bit different here. So what count does, notice we're getting now 2 columns back instead of just a single set of values. Before, notice we got a series object back, like value counts. We got a series back. Now we're getting a data frame back that's telling us the number of non-missing values in each column. So notice in this first column, there's only 1 non-missing value. In this column, we have 2 non-missing values, right? Down in this column, we have 3 non-missing values. And so that can also be useful in some instances. It would have been nice if this was called something like count not NaN. It's unfortunately just called count, which can be a little bit confusing, but just keep in mind that's what's going on. I always like my code to read really explicitly. If I'm trying to count the not NA elements, I want to usually say that. Fortunately, we're stuck with count, okay? Personal preference. All right, filter. I'm going to show you the diagram for filter first, and then I'll actually go write out what it's doing under the hood. But filter is very powerful. Filter is very powerful. So instead of aggregating our data after grouping it, we can actually filter out particular groups. So let me show you what's going on here. First step is exactly the same. We're grouping by the letter here, A, B, and C, same as before. But now we're doing dot filter with some function as opposed to dot aggregate with some function. And then what is that filtering function? We're seeing that lambda function again, okay? We're seeing a lambda function, an anonymous function, a sort of one-off function that's not stored in memory after it's used, okay? Where that lambda function is going to take our subframe, remember these are subframes, SFs are subframes, DF usually refers to the original data frame. We're going to take our subframes, we're going to go grab the num column in that subframe, we're grabbing that number column, we're summing it up, and we're checking if it's bigger than 10. So notice this function is not returning a series or any fancy object. It is literally returning true or false. And it's just a scalar, right? It's just a single value here. There isn't any series. This filter function is just returning a single true or a single false for each subframe. If it's true, we keep the subframe. If it's false, we don't keep the subframe. That's it. That's it. So notice those two middle subframes, the sum of all of the values was greater than 10, and so we kept them in the data. We kept them in the data. For the other subframes, the sum wasn't greater than 10, and so they got filtered out. Okay, that's filter. That's filter. So if we actually just go write this out in English, what's going on here? I think the diagram's more helpful. But we're grouping by something, and then we're doing dot filter with some function. Okay, filtering is done on the group level, not on the row level. Unlike Boolean indexing, we're filtering just on the group level. It's going to apply some function that either returns a single true or a single false for each subframe. Not a series, okay? Literally, yes, do we include this group? Or no, do we not include this group? Okay, no, do we not include this group? And then there's a little note at the bottom about how indexing changes, but a lot of that I like to discover as I actually work through code and sort of handle on the fly. Okay, that's filter. Let's try a harder Slido here. Give this a go. Feel free to talk with your neighbor. What's going on here? And I'm going to try not to show the correct answer this time. Okay. And I just want to remind folks too, Slido, not only can you answer Slido questions like this, but you can ask questions during the entire lecture that are going to be answered for you by ATA within a minute or two most of the time. So feel free to ask questions, clarifying questions as you go along. That code in the top right is really intended so that you can get like just-in-time help during the lecture. And obviously you can also raise your hand. You can also raise your hand. So we're looking for names that only appeared for the first time after 2010. So these are like super modern names by like Blaze and like Lightning, right? So let's see if we can go find them. So which of those is going to work? Let's go take a look at the demo. So we go to the demo. Let's go down, down, down. Slido. Okay, we want to get all the rows of baby names that contain names that appeared for the first time after 2010. So if a name only shows up after 2010, then that means the values in the year column for that name will either be 2011 or later, right? They're only going to be 2011 or later. We're not going to have any rows where we have that name in the year is 1967, right? Because that name is only showing up for the first time in the data set after 2010, okay? So in this first case, we're saying, okay, well, group by name, and let's go move all the way down here because this is not behaving. There's our Deborah plot. Okay, hold on. Okay. So in the first case, we're grouping by the baby name, the actual name, and then for each of those name groups, so remember a subframe with the name for a bunch of years, one name for a bunch of years, one name for a bunch of years, we're only going to keep the subframes where the minimum of the year is greater than 2010. And so if we think about what we just said before, a name only appears after 2010 for the first time, then indeed the minimum year for that name has to be after 2010, right? It has to be after 2010. So this first one should work out okay. And let's see what kind of names we get. Yeah, those look like 2010 or later names, right? We get some funky spellings, all this stuff. Okay, so that's a nice way to check that we're probably correct here. What about the max after 2010? So this is a little different. This is asking the question, well, when was the last time the name appeared? The last time it appeared is after 2010. All this means is that somebody has the name, you know, more recently, last 15 years. So Mary, Helen, sure, I know young Marys and Helens. Okay, and then these last two are actually going to throw errors. They're actually going to just throw errors. Why are these throwing errors? So remember that this filter function has to be passed a function that returns either a single true or a single false. A single true or a single false for each subframe. In this case, we're taking the series with the year and asking, is that series bigger than 2010? That's going to give me a Boolean series of true and falses, right? That's going to give me a Boolean series. That is not a single true or false. Similarly, down here, same exact problem on that side, and then there's really no reason for us to be grouping by year in this case. There's no reason for us to be grouping by year. Okay, notice we can group by more than one value. We'll see that in a little bit. Okay, so going back to the Slido now, how'd we do? The toughie, go to work. Go to work, everybody. All right, that's our last Slido, I think, for the day. Now let's do a little bit of some more case study work. So let's go back to the elections data set. The elections data set. If we wanted to filter only to the elections where there was no majority of votes, there was just a plurality of votes, so the maximum winning percentage is less than 45%. So for example, Clinton, in his 92 election, we had Ross Perot also running. It was Ross Perot, George H.W. Bush, and Clinton. Clinton won with less than 50% of the vote, far less than 50% of the vote. And so we'd hope that that one would show up in this data set. Okay, and here's one way to do it. We can use the filter function, and all we're saying is, okay, well, for each year, for each election year in this case, for each election year, we only want to keep the election years where the maximum winning percentage was less than 45. So essentially the person who got the most votes, the candidate who got the most votes, got less than 45% of the total votes. Okay, another application of filter. So let's do a little puzzle here. So the best election, we're going to define, again, what was the best election for a party? You know, kind of depends. What does best mean? Let's define it. Let's pick a metric, big part of being a data scientist. Let's say it's the election that has the highest percentage of votes for each party, including third parties, right? Including third parties. So for example, 1964 was a Democratic landslide. Lyndon Johnson won more than 60% of the votes. So we want to go write a query in pandas that returns this data frame. Later in the class, we'll use SQL. We can do the same thing in SQL. If you ever learn R, you can do the same thing in R. Okay, how do we go find this data frame? So one thing we could do is we could try this code. Let's try this one attempt. Okay. Maybe we could take 30 seconds to talk with your neighbor here. If we use this approach, it looks like Woodrow Wilson in 2020 had a really big win. Why is this happening? Chat with your neighbor, maybe 30 seconds here. What's going on? What's going on? So when we don't specify which columns to aggregate, Pandas is going to attempt to aggregate all of them, right? If we don't specify which columns to aggregate, Pandas is going to attempt to aggregate all of them. And it's not going to aggregate them with reference to each specific column and kind of keeping things together. It doesn't know what an election is, right? Pandas doesn't know what an election is. It's just looking at columns here. And so it's going to go compute the max of each column. What is the maximum year for the Democrats? Well, the last time they showed up when this image was produced was 2020. Okay, the candidate with the name that is last alphabetically is Woodrow Wilson, right? The highest popular vote that was ever achieved in this data set was Joe Biden in 2020, okay? And so, again, another thing to remember is like your code doesn't have context for an actual problem. So if something doesn't seem to be working correctly, don't assume that it sort of understands the context of your data set. Another common pitfall. So how do we fix it? So again, this is just an explanation that I just said here. So let's try this approach, this sort of visual approach here. So what if we did this? What if we first sorted our data? So we're going to sort our data without grouping it. So notice that first data set, it's not grouped. These are just a ton of rows. We're going to sort by the percentage. Okay, and so we end up at the very top. That turns out that was the best election for any party, that 1964 Lyndon Johnson election. And we're going to say ascending equals false. So we're sorting by descending percentages now, right? The Green Party in 2004 did the absolute worst of any party ever in any election. Okay, and then now we're going to group by party. Now we're going to group by party. And of course, each of these subframes would be a little bit bigger, right? There'd be a lot more Democrats. There'd be a lot more Republicans. There would be a lot more Green parties. And there'd also be a lot more parties otherwise, but we're just seeing a little snippet here. But notice what happens here, and this is a nice thing to take advantage of. When you group, order is preserved. When you group, order is preserved. The data set doesn't get shuffled on the group. So notice those first two rows for Democrats end up in the same order, right? These end up in the same order. They don't get shifted around. Some Green Party from inside here comes in, and the Green Party at the very end is at the bottom. So if order is preserved, this is really nice, because if you ever want the maximum of group, you can sort, slice off the top. Slice off the top, right? We can use head 1, or we can use this first function if we want. And that first will pull off the very first row of each of those subframes. Okay? This is exactly what we just did, now just in words. I like the visuals. So we're going to group by party. We're going to group by party after this. We're going to first sort the values, by percentage. So the first thing we do, we just saw, we're going to sort by percentage. Again, that Lyndon Johnson election is at the very top here. Okay. And then we're going to group by party and slice off the first value in each party. We're going to slice off the first value in each party. Okay, and notice in this case, we didn't actually even specify that we wanted the first of the percentage. We just said the very first element, But that's fine because each of the rows in these subframes is a whole election that didn't get all split up. So we're just grabbing the very first element of each of these subframes. And now we have the data frame that we wanted from the very beginning. The Democratic election is right there. Okie doke. Two other topics I want to talk about. I think we're wrapping up. Yeah, so just two other topics, things I just want to briefly mention. They're pretty quick. They're pretty quick. I know we've got about 15 minutes. We've got plenty of time here. So the first thing I want to talk about are pivot tables. Now, pivot tables you learned about in Data 8. Pivot tables are also really, really common when you're at, let's say, like a finance firm and you're building a lot of things in Microsoft Excel. Okay, pivot tables show up a lot there. Now, one thing I just want to mention about pivot tables is that they really exist for an end user. And I'll explain what I mean by this. They sort of exist for an end user. When you're actually doing exploratory data analysis and you want to work with a table and make a plot or do more analysis, pivot tables kind of end your analysis. And I'll explain why in a sec. So let's say we want to figure out the number of babies born with each year, for each year and each sex. So notice I have each of the years here, and we have each of the sexes. We have something that's what's called multi-indexed. Multi-indexed. So instead of just having a single index, we have, let's see, can I draw a circle today? I might not be able to draw a circle today. There we go. We have a multi-index. Okay, we're essentially indexed by a combination of both year and sex. Don't worry about the details of that for now. We'll go over it later in the class. But we're computing now the sum for each year and sex of the count column. Okay, that's all. Just the number of babies born who are male and female in each year according to this data set. And then we're just grabbing the first 6 rows. So this multi-index, okay, it kind of works. We can read this data set and like read it relatively easily. But another way to display this data is with a pivot table. So this is exactly the same way to show the data we just saw. So notice the very first element of this pivot table has the count 5950, 1910 for female. If I go back a slide, 1910 for female, 5950. But instead of indexing everything on the left side as an index, with a pivot table, you can now place each of the groups on its own dimension here. So we have year on the left here, and then we have F and M on the right. And this is a very convenient way to display your data if you're interested in easily visually comparing the number of babies born of each sex each year. But when it comes to doing actual plotting and more analysis, I just want you to know this is not a great thing to do. It'll sort of end your analysis. That can often be useful. So if you go to this link here, this is like an ACT score lookup table that's sort of in this pivot table format. Pivot tables are like a nice thing to hand off as like a product to somebody or as a dashboard for keeping track of what's going on in a company. Okay, they're very much like an end result. Okay, so I just want to show you how to make them in the class, but just keep in mind when you're actually plotting, you're not going to be working with pivot tables usually. And so how does a pivot table work? It contains exactly the same information as the group by, it's just organized differently. And so we provide exactly the same information to the pivot table as we did to the group by, just in a different order. So we're saying in the index on the left side, use year. For the columns, for the second group, use sex. Those could have been flipped, right? We could have had 2 rows for male and female and then had all the years going over the columns. Okay, the values that we want to aggregate are count, and then the aggregating function we want to use is a summation. This is the same information that was provided to group by, it's just giving us a slightly different output now. That's easier for us to read, again, worse to use later on in analysis. Okay, exactly the same information though. And then we can also do pivot tables with more than one value, more than one index, more than one column, or more than one aggregation function. These are very flexible. You can play around with them a lot. Here's one example. Instead of just getting count, let's do count and name, and we're still going to do the max. So that'll give us the last element. Notice all that happened here is we have our original pivot table for count, and then we effectively have a second pivot table on the right here for the name. And so I recommend you play around with this on your own. You can add in additional columns. You can duplicate columns and see what happens. You can add in more aggregation functions. But I just want to expose you to pivot tables so you know what's going on. A pivot table is simply just a group by operation organized in a nice way. That's it. Understanding group by, I think, is more fundamental. All right, and then the last thing I want to show you are joins. And we're going to do more with joins later on. When we get to SQL, we're going to learn about all different kinds of joins: left join, right join, outer join, left inner join, left outer join, all this stuff. Today, we're just going to learn about one join, effectively called the inner join. In the slides, it's called merge. Okay, joining tables. How do we join a table? So let's say we wanted to play around with both of our data sets together here. We want to play around with both of our data sets. So let's say we want to know what's the popularity of different presidents' names. And this is always kind of an interesting thing to do with the baby names data set, is you can plot a particular name and then you can see interesting spikes. Like the name Bruce will like spike when like Batman is released. You know, there's lots of interesting things here. And so with presidential elections, it's the same idea. You know, Donald probably became a more common name more recently because Donald Trump was elected more recently, right? So suppose we want to know the popularity of each of the candidates' names. Okay, Dwight, I don't know any Dwights. I guess I do know some Dwights, but they're older. Okay, there's probably not a lot of Dwights more recently. But if I wanted to filter my baby names data set to just names that are in the president's database, I could use a filter like we saw before, but another thing we could do is a join. Always a couple different ways to tackle a problem. And so I just want to show you, what do I mean by join? So here's the baby names data set for 2022. All I'm doing is taking baby names and filtering it such that the year is 2022. Okay, nothing fancy here. And what I'm going to do is join that to the elections data set. So here's the elections data set, except now I'm adding a new column. I'm saying in the elections data set, create a new column called first name. I'm going to create that column by starting with the candidate's full name. I'm going to use that string accessor that I said we're going to learn more about next week, take for granted for now. We're essentially telling pandas, hey, we're about to use a string function. So when you use .str, it opens up this big library of string functions. The string function we're going to use is split. By default, it'll split on spaces. That's why we're not specifying how to split it. By default, it splits on spaces. And then we're using the string accessor again to index into the resulting split object and pull out the first name. Right? So we start with Andrew Jackson. We're going to split into two different groups. Okay, based on that space, we're then going to grab the first name that comes in that group. Don't worry too much about that code for now. Again, we'll see that more in lecture 6. Okay, so now we have all the first names, and now we can join them. Now we can join them together. Again, something you saw in data 8. Now we know the pandas syntax for it. What we're going to do is we're going to use this pd.merge function, pd.merge, so pandas.merge. The left data frame that I'm going to merge on is the elections data set. Okay, left side is the elections data set that now has this nice first name column. The right data frame is going to be that baby names 2022. So I have a left data set and a right data set. I could have done it in the opposite order too. Typically, the left data set is your primary data set. The right data set is something you're sort of tacking on additionally. And then how are we going to actually merge these two data sets? I want you to only keep rows where the first name from the left data set, so that is the first name of the presidential candidate, is identical to the name in the right data set. So the name in the baby names data set. And so notice what's happened here. In all of the Benjamin rows, okay, I've matched identically. Notice the row actually got duplicated. I've matched to any row in the right data set that has a Benjamin in the name column. Okay, and notice the row automatically got duplicated for me. What if there were multiple rows in the baby names data set that would match? You would get every possible combination. Okay, it can really explode when you have these multiple matches. Okay, but notice the same thing has happened now in all of these other cases, right? We only have one Clinton row. We only have one Daryl row. Okay, we have two of these James rows. Okay, but that's like the basic idea of merging. Only keep rows that match based on one or more columns. But then there's different kinds of merges where we can say, you know, keep everything that doesn't match in the left data frame, keep everything that doesn't match in the right data frame, all different kinds of things. We'll learn about those later in the class. For now, we're just going to work with this idea of merging, where we only keep rows that exactly match one another. And there's lots of cool things you can do with merges as well, like fuzzy merges. With machine learning, this gets a little bit easier. With LLMs, it gets easier. Where let's say you have two data sets where you have like high school name in one data set, high school name in another data set, and they're written a little bit differently. It can figure out that they should be matched beyond the scope of Data 100, but just something to keep in mind. Okay, all right, and so that's a join. I think that takes us to the end of the lecture. I just want to show you there's another way to do this. As usual, there's always a couple ways to do this. You can also write this in sort of that sentence notation where you chain together operations. So instead of using this outer pd.merge function, you can start with the elections data set, and you can say start with elections and then merge the baby names data set and provide exactly the same arguments. Okay, another way to do it. Just another way to do it, whatever sort of feels more natural. If you want to write a long chain, the second way is probably more helpful. Okay, I think that takes us to the end, but I'll go ahead and leave this slide up for people to take notes. I will see you all on Monday. Congrats on finishing week 1 of Data 100.